So in this lab, we'll be using equilibrium to help us go through the lab. And the interesting thing about equilibrium is that it's a reversible process. So in solution, you have both reactants and products at the same time. And depending on what's called the equilibrium constant, which we'll talk about in just a moment, the size of the equilibrium constant will tell you whether or not there's going to be more reactants at equilibrium than products, more products at equilibrium than reactants, or a roughly the same amount of both at equilibrium. And so, for example, if we look at some types of equilibrium processes, we have, dissolving oxygen in lake water. So we have O2, which is a gas, plus H2O, or we won't put H2O, it's O2 aqueous. And we have the double-headed arrow. So when you see this double-headed arrow, it means something is reversible. So when oxygen goes into the lake water, there's also some oxygen coming back out of the lake water at equilibrium. For example, if we dissolve sugar in water, we have sugar, which is a solid, and then we have sugar, which is aqueous. And so at equilibrium, we have a balance between the two. There's sugar going into solution and sugar coming out of solution. So again, that double-headed arrow means that it's reversible. Both sides of the reaction are present. And so with this, we get dynamic equilibrium, which means the rate of the forward reaction is equal to the rate of the reverse reaction. So if you remember in the last lecture, we talked about rates of reaction. And so what it would be is that the rate of the forward reaction which is the K times O2 gas raised to the M is equal to the reverse reaction which, as we talked about, would be and so this is just showing that at equilibrium, the rates of the two reactions are equal. And so what we'll be doing this week is what we'll be doing in this lab is seeing what will affect equilibrium. So we apply disturbance to equilibrium. How will it adjust to reestablish equilibrium? So again, as I just said, with the dynamic equilibrium, we have the double arrows, which tells us this is a reversible process, and that at equilibrium, both sides, the reactants and the products, are present. It's not just the reactants or the products. It's both of them are present, but depending on the equilibrium constant, they'll be in different ratios. So with equilibrium reactions, these tend not to go to completion. So before we talked about equilibrium in previous chapters, the reactions we wrote were completion reactions. So you only see the single-headed arrow, whereas when you see the double-headed arrow, these are not go to full completion, because if it went to completion, all the reactants would be converted into products. So these are called incomplete reactions. So there's going to be some reactants left over that are not converted to products when equilibrium is established. So you're going to be able to measure the amount of reactants and products present at equilibrium. And so you may say, well, how do we know when equilibrium is achieved. That could be from a color change, which is maybe what we'll be doing in lab. We'll be looking for color changes in the experiment. So with equilibrium, what happens is over time, if we have this reaction on the synthesis of ammonia, over time as we approach equilibrium, the concentration of the reactants decrease, shown here, while the concentration of products increase. And the products will increase and the reactants will decrease until equilibrium is established. And so that occurs when the rates of the forward and reverse reactions are equal. So again, as equilibrium is approaching, the reactants are decreasing in concentration and the products are increasing until they get to equilibrium. Once they're at equilibrium, there's no more change in the concentration of reactants and products. So depending on what the equilibrium constant is, which kind of gauges the equilibrium reaction, will determine whether it's going to be mostly reactant, mostly product, or a mixture of both at equilibrium. So how do we write the equilibrium expression? So here's a general form of an equilibrium reaction. The lowercase letters represent the coefficients. The uppercase represent reactants and products. And so to determine the equilibrium constant, which is KEQ, is going to be the concentration of products over reactants. So products go on top, reactants go on bottom, the concentration. And this is always for equilibrium expressions. You always put the products on top, you put the reactants on the bottom, and then the coefficients of the reactants and products are written as superscripts. So whatever number is in front of the reactant or product, we raise the concentration of that reactant or product to that. And this is how we determine the equilibrium constant, which is this big K here. Again, it's the concentration of products over reactants. So here we're using this reaction. We have N2 plus 3H2 gives us 2NH3. And this is referred to as a homogeneous equilibrium because the reactants and products are the same phase. And the way you know they're the same phase is because they have the same subscript next to their formula. So they all have G, which means it's a homogeneous equilibrium. So when you have a homogeneous equilibrium, everything is included in the equilibrium expression. And so what do is we take the reaction, we put the products over the reactants, and then the coefficients of the products and reactants become what we raise those concentrations to. Let's see if I have it. Yes. And so when we raise it, we get this as the equilibrium expression. So again, what we do is we take the chemical reaction, since this is homogeneous equilibrium, that means they're all gases. So they're all going to be either all gases or all aqueous. So the product we put on top, the reactants we put on the bottom, and then we raise the reactants and products to the power of the coefficient that's in front of them. So since there's a 2 in front of ammonia, we raise that to the second power. Since there's a 3 in front of hydrogen, we raise it to the third power. And so this is the equilibrium expression for this reaction. And again, equilibrium constant changes with temperature. So whenever you're obtaining the equilibrium constant, you also have to inform them what the temperature is, because at different temperatures you can have different equilibrium constants. But for homogeneous equilibrium, that means they're all the same phase, either all gases or all aqueous. You put the products over reactants and you raise them to the coefficient that's in front of the product or reactant. So when you're writing the equilibrium expression, it has to be done after balancing the equation. And for the equilibrium constant, it has to be specified at a particular temperature, because with the change in temperature, you can change the equilibrium constant. And then we put the reactants and products in brackets to represent molarity. So that's why you see on the previous example, everything was written in brackets, because we're referring to them as molar concentrations. Now, the equilibrium constant itself are unitless, so there's no units for the equilibrium constant. Now, this last bullet is very important. It says only the concentration of gases and substances in solution are shown. So that means if it has a subscript of a G or a Q, it's shown in the equilibrium expression. Only those two types of phases. Pure liquids and solids are not shown. That's very important. So if you have a L next to a reactant or product, or an S, those are not included in the equilibrium expression. Only gases and aqueous species are included. Solids and liquids are not. So you would omit those from the equilibrium expression. Now for homogeneous equilibrium, where they're all the same phase, they're all either going to be all gases or all aqueous. So those you don't have to worry about. It's the heterogeneous equilibrium, where there are different phases that you need to watch out for if you see any liquids or solids. Those are not included in the equilibrium expression. So here we have this reaction involving the synthesis of HF. Again, this is a homogeneous equilibrium, which means all the reactants and products are gases, so there's no solids or liquids present. And so again, we put the products over reactants and we raise the product or reactant to the coefficient in front of that product or reactant. Now, if it was a heterogeneous equilibrium like this, here you'll notice that we don't have just all aqueous. We have aqueous, we have solid, we have gas, and we have liquid. So you see MnO2 is a solid, then we have an aqueous, Cl minus is an aqueous, Mn2 plus is aqueous, and Cl2 is a gas, and then we have another liquid. So since manganese oxide, manganese 4 oxide is a solid, it is not included in the equilibrium expression. Since H2O is a liquid, it is not included in the equilibrium expression. And so that tells us that those two things do not, or those two species, the manganese 4 oxide and water, do not affect equilibrium. So that's why they're not included in the equilibrium expression. So again, this is a heterogeneous equilibrium where you have different phases of reactants and products. Just remember that solids and liquids are not included in the equilibrium expression. It's still done the same way with products over reactants. So this is important, interpreting equilibrium constants. And so that's the value or the size of K. And depending on the size of K, you can determine at equilibrium whether you're going to have a lot of product, lot of reactant, or a mixture of both at equilibrium. And so when your KEQ is roughly greater than 1,000, this tells you that at equilibrium you're going to have mostly product. And the reason is because, so if we look at the equilibrium expression, it's concentration of products over reactants. And so if our K is very high, that means we have a lot of products at equilibrium and very little reactants, so that we get a large K value. So again, if your K is very large, usually on the order of greater than 1,000, it tells you that there's mostly product present at equilibrium, and that's because when you have a very large numerator, very small denominator, you're going to get a very large result. Now, if you have a KEQ less than, say, 10 to the negative 3, this tells you that you're going to have mostly reactant at equilibrium and very little product. Because again, if we write the equilibrium expression, it's a concentration of products over reactants. And so if K is very small, that means we have a lot of reactants, very little product. So therefore, at equilibrium, there would be mostly reactants present. Now, if it's roughly between 10 to the negative 3 and 10 to the third, we kind of say that the reactants and products are relatively the same amount of concentration. But for example, if it's 10 to the negative 1, 10 to the negative 2, 10 to the negative 3, we would say reactants are slightly more favored than products. Whereas if it was 10 to the 2, 10 to the 3, we would say products are slightly more favored than reactants. But basically, they're kind of the same amounts of each, just kind of tilting in one's favor, depending whether it's less than 1 or greater than 1. And so this is how you can determine what's going to be present at equilibrium based on the value of the equilibrium constant. So now if you've been not paying attention, this is important to pay attention here, because we'll be talking about LeChatelier's principle, which is the focus of this lab. And so LeChatelier's principle states that if a stress is applied on a system at equilibrium, it's going to respond by way of altering the equilibrium composition to minimize that stress. So for example, if we have N2 gas plus 3H2 gives us 2NH3. If, for example, we increase the amount of N2, so we apply a stress such as adding a reactant, how will equilibrium respond in order to reestablish equilibrium? And so as we'll learn, when you add a reactant to a system already at equilibrium, it's going to shift to make more product. Another example could be if we decrease the amount of product, how will that stress be minimized in order to reestablish equilibrium? So if we remove a product, it's going to shift to make more product. And so when we call stressed, one way you can stress the system is by adding reactant, adding products, or removing reactant, removing products. Another way is to change the temperature. So if you increase the temperature or decrease the temperature, that can apply a stress. And the other stress is changing the volume of the system, either increasing the volume, decreasing the volume. These are all different stresses we can apply to a system at equilibrium. So the first one is adding a reactant or product. So if you add a reactant, it's going to shift to make more product until equilibrium is reestablished. Whereas if you add a product, it's going to shift to make more reactants until equilibrium is reestablished. So here if we add more NH3, NH3 is a product. So since we're adding, we're increasing NH3, it's going to shift, as they say, to the left. It's going to make more reactant. Now if we add more, say N2, since N2 is a reactant, since we're adding more reactant, it's going to have to shift to make more product. And the reason is, remember that K is concentration of products over reactants. And so if we increase the reactants, well then the system has to make more product to increase the products as well so that we can still maintain the same value of K. So that's why when you increase the reactants, it shifts to make more product until the ratio gives us the same K for that reaction. So again, if you add a product, it's going to shift to the left, aka add more reactants. If you add a reactant, it's going to shift to the right, aka make more product. Now if we remove reactants or products, we're decreasing the concentration of the reactants or products. So whatever side we're removing from, it's going to shift to that side. So for example, if we remove N2, which is a reactant, say we remove the concentration of N2. So since we're removing a reactant, it's going to shift to the left to make more reactant until equilibrium is reestablished. Whereas if we remove product, in this case ammonia, and since we're removing a product, it's going to shift the reaction to the right to make more product until equilibrium is reestablished. So again, just to kind of recap, adding a product or adding a reactant is going to shift the reaction to the opposite side. If you remove a reactant or remove a product, it's going to shift the reaction to the same side. So this is one way a stress can be applied, is by adding a reactant or product or removing a reactant or product. And so here if we look at the effects of concentration, we see that when we have more of the reactant is red, when it's more of the product is yellow. So in beaker A, since it's orange, this means it's a mixture of red and yellow. So that tells us we're at equilibrium. But as we go to B, you see what's happened is it shifts to the reactant side because, again, the reactant is red. So if our solution turns red, that means that it's making more reactant to reestablish equilibrium. Whereas if we see the beaker go yellow, that means that in order to reestablish equilibrium, we're going from red to making the solution more yellow. So that means there's more products present at equilibrium than reactants. So by looking at the color change, we can determine whether there's more products present at equilibrium, more reactants, or similar concentrations of reactants and products. So if we did this experiment and we got an orange color at equilibrium, that would tell us that, hey, there's relatively the same ratio of reactants and products. But if we did this, we added something to this reaction equilibrium and the solution turned red, that would tell us that it shifts to the reactants because now we have the red color is more predominant meaning there's more reactants in solution than products. But then if we take that same reaction in equilibrium and disturb it so that it makes more product, then yellow is the predominant color because now there's a high concentration of products and very little reactants. So by looking at the color change, you can determine whether it's which side of the reaction is more predominant than the other. So the other type of way we can disturb equilibrium is by affecting heat, aka increasing or decreasing the temperature. And so here we have this reaction involving the synthesis of ammonia. Now this is an exothermic reaction. This was touched on in the last lecture, but exothermic means it releases heat. And so when you see heat as a product, it's exothermic. Now the way you think of the effect of heat is thinking of heat as a reactant or a product. So imagine we increase the temperature So if we increase the temperature of an exothermic reaction, we want to know which way will the reaction shift. And again, when you increase the temperature, what you're doing is you're adding heat. So if we're adding a product, it's going to shift to make reactants. So when you increase the temperature of an exothermic reaction, it's going to shift to the left, back to the reactants. But if you, for example, if we decrease the temperature of an exothermic reaction, then that means that what we're doing is, if we decrease the temperature of an exothermic reaction, we're removing heat, and heat is a product. So therefore, since we're removing a product, it's going to shift to make more product. So it's going to shift to the right, back to products. So to give you maybe a very rudimentary example of this is when you make Jello. You know, they always say put Jello in the refrigerator so it can solidify. And so what happens is the solidification of Jello is an exothermic process because the Jello releases heat, causing it to solidify. And so since it's an exothermic process, when we put it in the refrigerator removes the heat from the Jello, which causes it to shift and make more Jello, aka solidify the Jello in that bowl. And so that's an example, if you want to say, of a common life example of LeChatelier's principle in action. Because the Jello is exothermic process, the refrigerator removes the heat from the Jello, making the reaction shift to the right to solidify more of your Jello over time. Whereas if you kept the Jello out on the countertop, it would take a very long time to solidify. So again, this is for exothermic reactions. We want to make sure that we remember exothermic heat is a product. If we increase the temperature, it's going to shift to the left. If we decrease the temperature, it's going to shift to the right. Now, endothermic reaction, we treat heat as a reactant. So it's the opposite of exothermic. So you see here, heat is listed as a reactant. And again, we can increase the temperature and we can decrease temperature. So if we increase the temperature, that means we're adding more heat. If we're adding a reactant, it's going to shift to the right to make more product. So what happens is, as it's established in equilibrium, the concentration of reactants go down, the concentration of products go up until equilibrium is reestablished. Now, if we remove heat, that means we're taking heat out, and heat is a reactant, so we're removing a reactant. So we decrease the temperature. It's going to shift to the left, make more reactant. So whether or not your reaction is endo or exothermic will dictate when you increase temperature, which way will it shift, or when you decrease temperature, which way will the equilibrium shift. And the last one is the effect of pressure, or you can vice versa, you can say volume. They're interchangeable because from Boyle's law, so with the effect of pressure, or you can say the effect of volume, they're inversely related. So what does that mean? It means if we increase pressure and it shifts one way, when we increase volume, it's going to shift the opposite way. Now, pressure volume only is affected by equilibrium if there's at least gases present in the reaction. So if you look at the equilibrium equation and you don't see any G subscripts, pressure will not affect equilibrium. So there has to be at least one gas present on either side of the reaction for pressure or volume to affect equilibrium. It only works with gases. It doesn't work with anything else. And so, for example, let me write a reaction here. Well, that one won't work. Let me change this to page 6. So here we have this balanced chemical equation. It's at equilibrium. And so you see we have a variety of gases. And so on the reactant side, we have a total of 9 moles of gas. Again, you only count the coefficients of the reactants that have a subscript of G. So on the reactant side, we have 9 moles of gas. On the product side, we have a total of 10 moles of gas. And again, the way I get this is I look at the reactants and products with the G subscript, and I add up their coefficients. So now for this reaction, it says pressure goes up, it shifts to the side with the less moles of gas. So if we increase pressure, the direction it's going to shift, in this case, it's going to shift to the left, to back to the reactants, because the reactants have fewer moles of gas. And again, it won't always be the left. It depends on which side has the fewer moles of gas. And the same thing would happen if I decrease the volume would shift to the side with fewer moles, or excuse me, the equilibrium would shift to the side of fewer moles of gas. So this one would also shift to the left. And again, that's because they're inversely related. So if I increase pressure, it's the same as decreasing volume. So if I increase pressure, it's going to shift to the left. If I decrease volume, it's also going to shift to the left. Now, if I decrease pressure, or if we say increase volume, it's going to move to the side or shift to the side with more moles of gas. So in this case, it's going to shift to the right. And so that's why you know the effect of pressure or volume. For pressure, when you increase it, it's going to shift to the side with fewer moles of gas. If you decrease it, it's going to shift to the side with more moles of gas. Because then as you decrease pressure, there's more space because the volume increases, so there's more space for gas molecules. And so again, just to recap, the three things we talked about that affect equilibrium or can stress equilibrium are concentration, removing or adding a reactant or product, changing the temperature, aka adding or removing heat, and affecting the pressure of a system that contains at least one gaseous reactant or product. So here, for example, we have this reaction N2 plus 3H2 gives us 2NH3. If we increase the pressure, which way will equilibrium shift? Again, the reactants have 4 moles of gas. The products have 2. So if we increase the pressure, it's going to shift to the right. If we look at the second example, we have 2 moles of gas on the reactant side, 2 moles collectively on the products side. And if we increase the pressure, which way will equilibrium shift? This will be no change, because if you have the same number of moles of gas, pressure will not affect equilibrium. So since there's both 2 moles of gas on both sides, there's going to be no change in equilibrium. So it wouldn't do anything. Now, we have talked about a catalyst. We mentioned a catalyst in the last lecture dealing with kinetics, how it lowers the activation energy of your reaction. Now, a catalyst has no effect on equilibrium. So the thing that the catalyst does is, again, it lowers the activation energy so that the forward and reverse reaction can continue with easier. So it doesn't prefer one reaction or the other. It just lowers the activation energy of that reaction so that now you can get to the forward or the reverse reaction easier. So anytime you use a catalyst, it doesn't affect equilibrium. The only things that affect equilibrium are, again, concentration, pressure, and heat.